Well, now let's try to use the intermediate value theorem to solve the second problem. Assuming the temperature varies continuously over space, prove that at any given time there are 2 points on the Earth's equator directly opposite one another that have the same temperature. Alright, well, just like last time, we're going to try and find a function to which we can apply the intermediate value theorem. But before we do that, we need to figure out what our variable is here. So let's draw a little picture of the equator. Okay. So you can imagine you're looking sort of down on the Earth from above the North Pole, so the equator looks like a circle. And one way of identifying the points on a circle is by their angle, right? So if you draw an angle theta here, counterclockwise from the positive x-axis, then you can identify this point right here by that angle theta. Theta is basically the longitude value of this point on the equator. So that's our variable, and our function, let's see, the problem tells us that temperature varies continuously over space. So we could let T of theta denote the temperature at the point at an angle theta along the Earth's equator. Okay. Now, what are we looking for here? We would like to find 2 points opposite one another where the temperature is the same. Another way of saying that is we would like the difference between those two temperatures to be 0. So it might be a good idea to define another function. Let's call it f of theta to be the temperature at the point with angle theta plus pi at the opposite end of the circle minus the temperature at the original point. Well, we don't actually know the value of that f anywhere. Lots of different things could happen for the temperature on the equator. But what we can do is consider the value of f at 2 opposite points and see how those compare to one another. So let's write down f of 0 and f of pi. F of 0 would be just t of pi minus t of 0, whereas f of pi would be t of pi plus pi is 2 pi minus t of pi. Okay, but an angle of 2 pi identifies the same point as an angle of 0, so this can be rewritten as t of 0 minus t of pi. And if you compare that to what we had up here for f of 0, it's just negative f of 0. Which is nice because now we have, two different places, 0 and pi, where the function f has opposite signs. Okay. All right. Well, before we use that, let's take care of one sort of simple case. What happens if f of 0 is actually just equal to 0? Right. Well then, by the definition of the function f, we see that t of pi minus t of 0 in this case would also equal 0. So t of pi is equal to t of 0. And in that case, we're done. We found 2 opposite points with the same temperature. So now let's consider the case where f of 0 is not equal to 0. Okay. Well then, since f of 0 and f of pi do in that case have opposite signs. We can apply the intermediate value theorem, right? Because this function f is continuous. It's the, let's see, t of theta plus pi is continuous because it's a composition of continuous functions. And then we have a difference of continuous functions gives a continuous function. So because f is continuous, we can apply the intermediate value theorem. And we get that there exists some c in the interval from 0 to pi. Whoops. Such that f of that c is equal to 0. Okay. And then, well, we can finish off just as we did up here. This means that in terms of t of c plus pi minus t of c is equal to 0. Or in other words, t of c plus pi is equal to t of c. Okay. So these 2 points at angles of c and c plus pi, which are indeed opposite from one another, have the same temperature. And that finishes the proof.